A solar storm, also known as a solar flare or coronal mass ejection, CME, refers to an eruption of high-energy radiation and charged particles from the Sun. These storms, which are driven by the Sun's magnetic activity, can have significant effects on the solar system, including disruptions to satellite communications, power grids, and even human health. To truly understand solar storms, it's essential to explore their causes, effects, and the science behind these powerful phenomena. The Sun's activity and solar storms. The Sun is a vast ball of hot, ionized gas, primarily composed of hydrogen and helium, and it generates energy through nuclear fusion. Its surface temperature is approximately 5,500 degrees Celsius, 9,932 degrees Fahrenheit, but the temperature rises drastically as we move deeper into the Sun. The inner core is where nuclear fusion occurs, releasing massive amounts of energy. The Sun's outer layer, the corona, is a source of great interest to scientists, especially when discussing solar storms. The corona is much hotter than the Sun's surface, with temperatures ranging from 1 to 3 million degrees Celsius. This high temperature causes the corona to expand outward, carrying particles and magnetic fields into space. The solar magnetic field is a key player in solar storms. The Sun's magnetic field is complex and constantly changes. These fluctuations occur in an approximately 11-year cycle, known as the solar cycle, where the Sun's magnetic poles switch places. This cycle governs the frequency and intensity of solar storms. Types of solar storms. There are several types of solar storms that vary in intensity and nature. Solar flares, these are sudden, intense bursts of energy that occur in the Sun's atmosphere. Solar flares release large amounts of electromagnetic radiation, including X-rays and ultraviolet light. These radiation bursts can cause radio communication disruptions on Earth, especially in high-frequency bands used for aviation communication. Coronal mass ejections, CMEs. These are massive bursts of solar wind and magnetic fields rising above the solar corona or being released into space. CMEs carry a vast amount of energy and can be highly disruptive when they collide with Earth's magnetosphere. They are often associated with solar flares, though not all solar flares produce CMEs. High-speed solar wind streams. These streams of charged particles emanate from coronal holes, which are regions of the Sun's corona with lower density and temperature. While not as intense as solar flares or CMEs, these solar wind streams can still affect the Earth's magnetosphere and cause geomagnetic storms. How solar storms develop. Solar storms are primarily triggered by the Sun's magnetic activity. The solar magnetic field is highly complex and constantly shifts, creating regions of intense magnetic stress. Sometimes, this stress becomes too much for the magnetic fields to hold, resulting in an explosive release of energy in the form of solar flares or CMEs. When magnetic field lines near sunspots become twisted and tangled, they can snap and reconnect, a process known as magnetic reconnection. This releases vast amounts of energy in the form of radiation and high-speed particles. The particles from a CME or solar flare can travel through space and, if directed toward Earth, can have a range of effects. Impact on Earth. Solar storms can have a variety of impacts on Earth, from minor disruptions to significant damage. Some of the potential effects include disruptions to communications. The intense radiation from solar flares can interfere with radio signals, particularly high-frequency bands used for aviation and military communications. The ionosphere, a layer of charged particles in Earth's atmosphere, is affected by solar radiation, leading to communication blackouts, especially near the polar regions. Power grid failures. CMEs can induce electrical currents in power lines, which can overload transformers and cause widespread power outages. The most famous example of this occurred in 1989, when a massive solar storm caused a blackout in Quebec, Canada, leaving millions without electricity for hours. In extreme cases, large solar storms could cause damage to power grid infrastructure, leading to long-term blackouts. Satellite damage. Solar storms can damage satellites in space by exposing their electronic components to high levels of radiation. This can lead to malfunctions, failures, and a shortened lifespan for satellites. Solar storms can also increase the drag on satellites in low Earth orbit, altering their orbits and possibly leading to their premature deorbiting. GPS disruptions. Solar storms can affect the accuracy of GPS systems by disrupting the signals they rely on. This can cause errors in navigation, particularly for aviation and maritime operations. Radiation hazards to astronauts and aircraft. Solar storms pose a significant radiation risk to astronauts in space. The high levels of radiation from a solar flare or CME can be harmful to human health, leading to radiation sickness. While Earth's atmosphere and magnetic field provide some protection, flights at high altitudes near the poles can be affected by solar radiation. For astronauts outside Earth's protective shield, solar storms can pose severe health risks. Predicting solar storms. The ability to predict solar storms is an important area of research, particularly to mitigate their effects. Scientists study the sun's behavior and magnetic field to predict when solar storms might occur. They rely on observations from solar observatories like NASA's Solar Dynamics Observatory, SDO, and the Solar and Heliospheric Observatory, SOHO, which monitor the sun in real time. Additionally, space weather prediction centers, such as the National Oceanic and Atmospheric Administration, NOAA, and the European Space Agency, ESA, use data from solar observations to forecast solar storm activity. The data is analyzed using sophisticated models of the sun's magnetic field and its interaction with Earth's magnetosphere. However, predicting the exact timing and intensity of solar storms remains a challenge. While scientists can track sunspots and solar flares, the unpredictable nature of solar activity means that a complete and reliable forecasting system is still under development. Protecting against solar storms. To protect against the potential impacts of solar storms, various strategies are employed. Hardening satellites. To reduce the risk of satellite damage, space agencies are increasingly focusing on hardening satellite components against radiation. This includes using radiation-resistant materials and designing systems to shut down or shield sensitive electronics during solar storm events. Grid protection. Utilities and power companies are working on improving the resilience of electrical grids by incorporating protective technologies, such as transformer shielding and reliable backup systems. Space weather alerts. Governments and international organizations are working to improve space weather forecasting and communication systems. By issuing solar storm warnings, industries can take precautionary measures to protect critical infrastructure. Public awareness. Educating the public about solar storms and their potential impacts can help people be prepared for disruptions, such as communication blackouts or power outages. Conclusion. Solar storms are fascinating and powerful events driven by the sun's magnetic activity. Their impacts can be far-reaching, from communications disruptions to potential damage to power grids and satellites. While much progress has been made in understanding and predicting these phenomena, there are still challenges in fully predicting and mitigating their effects. As our dependence on space-based technologies increases, understanding solar storms and developing protective measures will become increasingly important for maintaining the functioning of modern society.
Thank you for watching. Please subscribe our channel.